So, good evening, everyone. Welcome to the very first live interaction session for this course, Waste to Energy Conversion. So, let's just wait for a few minutes for others to join before we begin our session for today. Meanwhile, since this is the very first live interaction session for this course in this semester, so I'd like all of you to either unmute yourself and then introduce yourself and just let me know your name and why you have opted for this course and what are you currently doing, or otherwise you can also mention the same in the chat box so that since this is a kind of a very since this course covers a very broad area of audience, so let's see what could be the expectations of people who have opted for this course. So yeah. Okay. So I think we can start our session. um, Let me just share my screen. I hope my screen is visible and I'm audible. Okay. So in case if you have any issues related to the audio, then please let me know. So I'm going to start the session right now. So I welcome you all to the very first live interaction session for this course, Waste to Energy Conversion, for the January to May 2026 semester. This course is offered by Professor Prasenjit Mondal from the Department of Chemical Engineering at IIT Roorkee under the NPTEL program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. I am one of the course members who will be conducting the live interaction session for this course in this particular semester. So, starting with the very first live interaction session, my very first question is, why are we supposed to basically study this particular course? Like, what makes you people interested in this course, or why is there is a need for this particular waste to energy conversion? Why do we need to convert the waste to energy? Like, what is the primary basis or primary need for such a thing, for such a process to evolve? Anyone from the audience? I just, can you please repeat yourself?
To achieve sustainability.
To achieve sustainability. So, when you say from the perspective of sustainability, what we actually mean is to basically reduce our dependency on the fossil fuels, which are already scarce, and then the quality of the fossil fuels are too degrading as the days are passing, and also to basically minimize the waste that gets produced, because if the waste keeps getting produced, then there needs to be a way to minimize the waste that gets accumulated. So for that particular, for these two reasons, one is to meet the energy demand, and another one is to basically go for the kind of a systematic waste management. We basically, one of the possible ways we choose is to convert these waste to energy. Now, so we will be having totally 8 weeks for this particular course, so 8 live interaction session. So before starting off with the today's one, what I would like to let everyone know is that we will first discuss, or you can say have a recap or a review of the concepts that was discussed in the course for around 30 to 40 minutes of the time, and then the rest, an hour or more than that, we will devote it to solving some of the numerical problems very similar to those that you will encounter in your assignments. So this is how, for the time being, I have it in my mind. So in case if you wish, then towards the end of the session, you are welcome to let me know your feedbacks and comments, so that we can uh, find a common ground and adjust things accordingly. So coming to the content, waste. So what is waste? What is the typical definition of a waste material? Or how do you basically determine whether a particular material is waste, or it, how do you determine a particular material is, how do you determine whether a particular material is a waste?
No economic value to the user.
That exactly, no economic value. Simply, to be more, to put it in a very very layman sense, it is something that is of completely of no use to us. It's something that gets generated in the process. It has no any value, no use, and that is what we usually call it as a waste material. And as such, when we speak about waste, there are lot of different ways. So now the question arises is that, I mean, as humans, we in our day to day life, we actually, what do you say, a lot of waste is usually generated by man. So we usually, out of any process, some amount of the material is going to go as a waste. So the question is, or if you say for any particular process, we will surely generate some amount of the byproduct that is going to get generated or going to be classified as a waste. So the question is, can all the waste that gets generated within the system be converted to energy, or is there, or is there any particular class of waste is what is only can be converted to energy? So that is what we will be primarily discussing in today's session, introduction and characteristics of waste material. What are these kind of waste material, or what are the kind of properties of the waste that are suitable so that they can be converted to energy. So as I said, all waste cannot be converted to energy. There are certain class of waste, those are those which will be useful to convert it into particular form of energy. And when we talk about that, it's not necessary that all the waste will be useful, and it is also not necessary that all the waste materials will go through a particular process to get converted to energy. Different waste, different properties, similarly different ways for generating the energy. Now, based on this, since as I said, waste, there can be a lot of different classifications of waste, different types of waste. The waste materials are typically classified primarily based on their hazardous nature. The very first one will be hazardous waste, and then the second one will be non-hazardous waste. So non-hazardous waste are something that do not cause harm to the human being or to the environment. In contrast, if you see, hazardous waste are nothing but they are the ones which are going to cause harm, or which really cause harm to the human beings as well as to the environment. So the hazardous waste are basically, there are four different kind of characteristics based on which you can actually classify a waste as a hazardous waste. Anyone with who knows that four different kind of parameters or the properties which qualifies waste as hazardous class class of material? What are the quality parameters to classify waste as hazardous?
Reactivity, toxicity,
Yes.
ignitability, and corrosivity.
Activity.
Four.
Yeah, these are the four. So let me just quickly write it down. So again, as I said, this is just as a kind of a recap, because in your assignments you may encounter these kind of questions, because it's going to be a mixture of both numericals plus these kind of theoretical multi-choice questions will be there. So just as a recap, we will use this 30 to 40 minutes of our time. Again, these are there in the course, this is covered by professor, so you can always revisit them and then kind of refresh your memory. So sorry, hazardous materials, oh sorry, hazardous waste, four parameters. First one is your toxicity, second one is ignitability, third one is the reactivity, and fourth one is the corrosivity. So these are the four quality parameters which basically qualifies your material as a hazardous waste material. Now this is one particular classification. Again, as I said, since there are a lot of different types of waste, you also have multiple classification for this solid for this waste material. So the first one is the hazardous waste. Sorry, first classification is based on whether they are going to be hazardous or non-hazardous. Second one is basically on their physical state. So the first one will be solid waste. Second one will be the liquid waste, or you can say the wastewater that gets generated from the factories or other kind of industries. And the third one is the gaseous waste. So what are the properties that we need to look for in each of them to basically qualify, or what are the properties that these waste materials in each of these classes of physical state should possess, so that we can, so that it qualifies them that they can be actually used for energy generation? Like if I take a solid waste, these must have these certain properties so that I can use them for energy generation. Yes, anyone? So based on the physical state, three classifications: solid, liquid, and gas. But what are the parameters which basically qualifies that these waste materials can actually be used for energy generation purpose? Eh, Anyone from the audience? So in order for a solid waste to be classified as a potential source for energy generation, it should have high heating value and high carbon and hydrogen content. Similarly, for a liquid waste, or you can say wastewater, it should have high BOD, COD, and TOC. And for a gaseous waste, it should have hydrocarbons, gaseous hydrocarbons, again, hydrocarbons and other fuel molecules. So in case of solid waste, they say that it should have high heating value, high carbon and hydrogen content. So what happens if it has other kind of elements, let's say nitrogen or oxygen? So in that case, does it mean that these materials will be regarded as not suitable for energy generation? In the first one, solid waste, we say that the waste material should have high carbon and hydrogen content. But a waste material can also have nitrogen, sulfur, and oxygen present in them. So, if they are more in proportion compared to carbon and hydrogen, does that mean that the material will not be suitable for energy generation? If yes, then why so? So keep this question in mind. We will return back to this while somewhere dealing with the characteristics of waste. Soon, within another few 10 to 20 minutes, we will reach that particular section. Now, for liquid waste, it should have high BOD, COD, and TOC. So, how many of you here know what is the meaning of BOD, COD, and TOC? Just the full form. BOD, COD, and TOC.
BRD is biochemical oxygen demand and COD is chemical oxygen demand.
And the TOC? So that's rightly said. So I'm not going to write it down here. And in case of gaseous waste, it's going to be hydrocarbons and other fuel molecules. So these are the certain, of course, apart from that, there are also other kind of, you can say, these quality parameters, but these values need to be high, so that suppose if you, for example, in case of gaseous waste, you're also going to have inerts and other kind of particulate matters that is going to be present in them. But then for a material of a, for a particular form of a waste to qualify as a energy generating material, you require these kind of you require these, you are supposed to concentrate on these parameters for their, for converting this waste material to energy. Now, this is one form of classification. Then the second one is, so now let's concentrate only on solid waste. So that's how the course actually progresses if you see. First, we basically talk about hazardous waste, then we talk about the physical state of these waste material. Then in, after discussing on this, we basically concentrate more on solid waste before progressing towards the liquid waste. So solid waste, again, it can it has its own classification. So anyone can quickly say what are the kind of classifications for a solid waste? Their classification based on what, like they're usually classified based on three different kind of parameters. One is based on source, second and third. So another one is based on their degradability. Am I right? Based on biodegradability, whether they are biodegradable or non-biodegradable in nature. And the last one is based on their usability. So based on source, if you see, you can classify them into three. One is municipal, industrial and agro-based. Then based on biodegradability, you can classify them as biodegradable, non-biodegradable. Then based on their usability, you can classify them into three different types. One is organic, inerts and recyclables. So here again there is one particular question that I want to ask. So in case of usability, we usually classify them as classify them into three different types. One is organics, recyclables and inerts. So here too we basically concentrate only on organics and recyclables. They are the ones that possess high heating value, and the inerts are usually not considered. Like for example, if a material is going to have, or if a waste material is going to have more amount of inert content, then that particular waste will be usually not suitable for energy generation purpose. So why is that so? What is typically the meaning of an inert material? Mm. Yeah, so that's exactly correct. Inert materials are something that that is going to remain stable even at very high temperature. For example, if you see nitrogen, that nitrogen remains stable even at very high temperatures. So they are not going to get combusted or react with oxygen and form some sort of oxide. So Due to that particular reason, inert materials have very low heating value because they are not going to combust and produce energy. So that is typically the reason why presence of an inert is often considered not suitable for a waste, not suitable for energy generation, and that particular waste material is usually not a good source for energy generation purpose. So why inerts are not useful for energy generation is basically because of their low heating value. So now coming to the solid waste management, there are two different ways in which you can actually do this management of the solid. The first one is either you basically collect all the solid waste that gets dumped and then take it to a particular location and then segregate, or segregate at the source. Here the question is, segregating at the source is far more convenient compared to collecting all of them and then taking to a particular place and then segregating it. So what is the reason that it is preferred to segregate the solid at source? Why are we suppose, I mean, why is it basically beneficial to do this segregation of solids at the source of, at the source where it gets dumped? Okay, that is one reason. Apart from that, anything? Sim- uh, it's simple that if you do it at source, the process is going to be more easy and it's going to be less expensive. Rather than, apart from one of the reasons what the what one of the attendees actually told right now, the other reason is going to be that it is going to be far more easier for you to actually do the separation process at the source rather than taking it somewhere and then doing it. And also, since you have to transport all the waste from one place to another location, it's also going to be the process is actually going to be expensive. So in order to minimize all these kind of constraints or the troubles that gets generated in case of the solid waste management system, the municipal waste usually gets segregated at the source itself. So usually this segregated materials are usually classified as recyclables, organic fractions, inert solids and hazardous waste. So again, as we talked just right now, the organics and the recyclables are something which is useful for, because they possess high heating value, so they are useful for energy generation. Inert materials, again, they have low heating value and often are again gets discarded as a waste. So in the way through which this solid the waste is usually converted to energy also is different. There are totally three different ways through which you can actually convert a waste material into energy. The first one is thermal conversion route, or you can say incineration, where you can actually put the material, burn it at very high temperature, and then whatever that amount of energy that gets generated through this process, you can use it, you can utilize them. The second one is through the chemical way, and then the third one is through the biological technique. So usually for solid waste management, we usually go for thermal conversion routes. For liquid waste, it typically goes through biological conversion routes. So that liquid waste or the wastewater that gets generated through the use of microbes and bacteria, a biological conversion process, the waste material is anaerobically digested and then it forms a sludge, and then that sludge is used for energy generation purpose. So it's not just that so the primary thing that I want to describe here is energy generation through waste material is not a single process, or it's not a simple process. It is complex depending upon the type of waste material. Not all waste materials can be converted to energy. Depending upon the type of waste material, the energy conversion routes vary, their processing varies, their management system or management technique varies. So having a very good understanding on how to process different types of waste material is essential, so that the process of converting the waste material into energy is more you can say is of more benefit to the people who work in that particular area. So this is about the classification of waste. Again, as I said, it's a very brief recap. For detailed explanation on all these, or if you have any queries, you are welcome to ask me right now. Or all of these are actually covered in the course. In case if you have not went through the course content, then please do make sure that you visit them. Now, before moving on to characteristics of waste, so the next part that we will discuss for the next 10 or 15 minutes is on the characteristics of waste. So, if you have anything that you would like to ask, then you are welcome to do so. Anyone has any particular thing to discuss? Oh, there is a. Oh, okay. Anything that anyone wants to discuss? I mean, related to the classification of waste. So let me ask one question before we actually progress. So as I said, a material for the thermal conversion routes, or you can say for the solid waste, the material should have high heating value. What about the moisture content within the material? Will it be useful if you have moisture in them? Like as I said, we should have higher carbon and hydrogen. But I mean, we kind of didn't discuss about oxygen, nitrogen, and sulfur. So, what will happen if your material is going to have more moisture within them? Will it be beneficial for the energy generation process, or will it be detrimental for energy generation? Specifically, when you're considering the thermal conversion routes, because moisture will play a very big role in making sure will play a very big role in affecting the efficiency of the energy that gets generated from the waste material. If you have high moisture content, if you have low moisture content or high moisture content, it will be a very crucial factor in energy generation process. So anyone with any this thing on whether a particular waste material should have high moisture content or a low moisture content for the energy generation process. Okay, one of them have told low moisture content. Can you explain why the moisture content should be low? What will happen if we have high moisture content? Because again, if the waste material is going to have high moisture content, then I need to do some drying process and then make it into low moisture content before I go for any kind of energy generation. And if it is simple drying, then it's okay, or otherwise I need to go for some other techniques, which is again going to be energy expensive. So why should the material have low moisture content? Yeah, that is true. So as somebody said, rate of heat transfer will be low. So that is correct. So if you have more moisture content, then more amount of the energy will be required to spend. You will have to spend more amount of energy in order to remove the moisture from the material. So the total efficiency of the process, if you see, will be less compared to if you use a dry sample or a bone dry sample, as we usually say in these kind of waste materials. So now let's move on to characteristics of waste. So as we talk about properties or characteristics of waste, always whenever we discuss, we for the two things that usually come to our mind is the physical properties and the chemical properties of the waste. So when I talk about the physical properties, what actually comes to your mind? As such, when I say physical properties, let's leave the concept of waste for the time being. As such, when I say the word physical properties, what are the kind of properties that actually strikes your mind immediately? You can speak out so that we can write, and then based on the and then we can actually discuss each of the physical properties to an extent in detail. So let me first write one thing. The first one is the morphology, or you can say the particle shape or size. Second one that comes to my mind is density. Third is, yes, physical properties. This, mm, okay, for a process it's fine. For a process, physical property, that is fine. But for a waste material, moisture, yes. Then here we will also introduce a concept so called as hydraulic conductivity. So we will discuss each of them. We have few questions also. So just have it in mind that we will be discussing about these four kind of physical properties. Or if you have any other physical properties, then please you're welcome to tell, so that we can think about how to explain them based on the waste material, or whether that physical properties is of importance when we is of importance with respect to this course. So as far as physical properties is concerned, these four: boiling point for that maybe in case of liquid waste, but again liquid waste we usually use biological conversion routes. As I said, the wastewater is biologically treated to form sludge, and then that sludge is actually used for energy generation. So again boiling point is a physical properties, but here for waste to energy conversion, that may not be a very important parameter. Apart from that, any other physical properties? Because waste water that we discuss, we do not go for thermal conversion routes, because if that material would have, if we would have used thermal conversion routes for wastewater, then boiling point is one of, it will be one of the important properties that we would look forward towards understanding. But since we go for biological conversion routes over there, that in that case boiling point is may not be a suitable property there, I mean, to discuss. I mean, it's not of much importance when we discuss about waste to energy conversion. Okay, so keep thinking about, are there any other physical properties which will be of interest for discussion. Let's move towards the chemical properties. So in case while dealing with chemical properties for any kind of waste, or you can say biomass as a waste, because typically the majority of the waste we use that comes out for energy generation, of a significant fraction of them comes from biomass. So for chemical properties, while dealing with chemical properties of the waste, we go for two types of analysis. The first one is the proximate analysis, and then the second one is your ultimate analysis. So what's typically the difference between this proximate analysis and ultimate analysis? There is one thing that actually differentiates this analysis part, or how you determine this constituents. For example, if you see proximate analysis, let me just zoom in this slide. So if you see in case of proximate analysis, we usually discuss about percentage of ash, percentage of moisture, percentage of fixed carbon, and percentage of volatile matter. Whereas in case of ultimate analysis, we usually discuss about percentage of carbon, oxygen, hydrogen, sulfur, nitrogen, even there also moisture, as well as some amount of the mineral matter that is present in them. So in order to you can say, in order to do this analysis, there is only one thing that actually we do different for understanding or for doing these analysis. So what is that we do? So, let me put it more clearly. So, for chemical properties, we do these two types of analysis. One is your proximate, and another one is the ultimate. So, while doing this analysis, both these analysis differ only in one particular aspect. What is that aspect which differentiate both proximate and ultimate analysis? In both the cases, you actually need to burn them. Otherwise, you will not be able to find the percentage of ash, moisture, fixed carbon or volatile matter, or the elemental percentage. But the way you burn them differs in both these cases, or to analyze these properties, you can say. What is that difference is what I am want to know. Anyone from the audience? Oh, I think there's a comment. Okay. Uh, when it is heated, how it behaves is proximate, ultimate analysis. Yes, that is the difference. Exactly what it is. Like in case of proximate, we do this. We find out the percentage of ash and what do you say, a fixed carbon, etc. But in case of ultimate analysis, we do elemental composition analysis. In both these cases, we actually heat the material, burn the material. But there is one thing that is different in both these cases. The way you burn them is actually different in both these cases. So that difference is what I am interested to know. So it's whether you do this process in the presence of oxygen or absence of oxygen. So in case of proximate analysis, you take your waste material and then you burn them in the absence of oxygen. Whereas in case of ultimate analysis, it's going to be in the presence of oxygen. Ye- Yeah, and then the fixed carbon percentage also for that. So for all these parameters to analyze, we need to actually do it without oxygen present. But for ultimate analysis, we require oxygen. So once you, yeah, yeah. So in case of ultimate analysis, when you burn them with the oxygen present, so the carbon will get converted to carbon dioxide, nitrogen will get to I mean their respective oxide forms, and then we will analyze their elemental percentages. So in order to do that, we use a analyzer which is called, any idea on how this elements are usually what do you say, elemental composition is calculated? You have an instrument to do this actually. The instrument, any idea on the instrument which is used for this analyzing the elemental composition in the waste? Jaldal's method, yes, but the Jaldal's method is specifically for nitrogen content, right, if I am not wrong? I'm talking about it's an analyzer. It's called as I hope some of you might have heard this name, something called CHNSO analyzer. So this analyzer, once you feed in your material, it will give out the percentage elemental composition of each of these elements: carbon, hydrogen, nitrogen, sulfur, and oxygen. So the ultimate analysis is usually performed by the CHNSO analyzer. Yes, Geldal's method, if I am correct, then it is used for determining the percentage of nitrogen. But again, we have there are different kinds of techniques actually to find out each and every element. Uh, for example, for nitrogen content, we use Jaldal's method, and for sulfur content, we usually use barium sulfate and then do titrations, and then from there we usually get the percentage of sulfur content. So like that, for each and every element, we have a typical process. CHNSO analyzer usually uses all of them, and then it gives out the result uh, as a chart. So this is the particular instrument name. Next, we have to discuss about something called fusing point of ash. Ash is nothing but something that is going to remain as a residue after burning the material in the absence of oxygen. What you are left out with at the end of this, I'd say I'll put the word pyrolysis process, is what is called as an ash. So that ash has certain properties. One of the properties that we are interested is to know is called fusing point of ash, and it is done at a particular temperature. So fusing point of ash is nothing but this ash material actually, after burning, after you obtain this ash, it basically forms a solid by fusion and agglomeration. So the ash, once it gets generated, it undergoes fusion and agglomeration, and that particular point is called fusing point of ash, and this happens typically at a temperature of 1100 to 1200 degree Celsius. But here I have a question: why are we supposed to be interested to know this fusing point of ash? I mean, what does it really benefit? I mean, by knowing this fusing point of ash, what benefits does it really bring to me, or what knowledge does it add to my analysis? Anyone who has kind of idea on this fusing point of ash? So look at it. This I will this we will discuss in the next live interaction session on what is actually the importance of fusing point of ash. Why we should know about this concept. So this too is about physical and chemical properties of the waste material. And again, I did check the comments. So yes, there are many physical properties like color, order, and taste. So all those are usually used during the segregation process itself. So when you talk about energy generation, we typically discuss about the morphology, density, moisture, and hydraulic conductivity. So anything that you would like me to they ask before we move towards the last concept? very short one on bomb calorimeter. So bomb calorimeter is very simple. As such as a process is concerned, it's nothing but this is how a bomb calorimeter looks typically. This is some this picture is usually is adapted from the course content. So if you see over in the course lectures also, you can see this picture. So in case of the bomb calorimeter, what we do is the material or the waste is usually kept inside the bomb, this container. If you see, if you are able to follow my pointer, then this is the bomb. Then the excess of oxygen is pressured within the system. The entire system is going to be submerged in this water bucket with a known volume of water. Once after this process is done, the bomb is usually ignited. So when the bomb is ignited, what happens is the material, so since excess of oxygen is already present within the system, and then you also have the material, when it is ignited, it releases excess of heat. So usually we cannot measure heat, right? Can we measure heat? I mean, as such, directly, can you measure how much heat gets released in the system? Heat is usually, heat cannot be calculated, heat cannot be measured. It is usually measured in terms of some other parameter, and from there we actually quantify that this much amount of heat is released. So how do you quantify, or what is that parameter which we use to quantify heat? Can you actually measure heat directly? Let's take for example, you take some amount of water and then you heat the water till it boils. Can you tell how much amount of, and then so once the boiling happens, heat is going to get generated. So can you say that how much amount of the heat is you have given to basically make the water boil? Can you quantify that? So usually you require temperature, right? So only based on the temperature we can say that this much amount of heat is released, or this fraction of heat is used up for the system. You need temperature. Temperature is the one that usually helps to quantify how much amount of the heat is generated in the system or used up by the system. So here, that is what I wanted to actually mention. So the bomb is ignited and then the bomb releases the heat. That heat is usually that heat is absorbed by the water or gained by the water in the surrounding, and the temperature of the water raises. Now based on that temperature change is detected by the thermocouple, and based on that temperature change we quantify that this much amount of the heat is released by burning that particular waste material. Concept is very simple. So you usually use a bomb and then you feed the bomb with raw material or the waste and excess of oxygen so that burning combustion can take place. Once you start burning them, you put this bomb inside a water bucket with a known volume of water. You burn the bomb or ignite the bomb. Once ignition happens, the material burns and it releases heat. That heat gets absorbed by the water. We know what is the initial temperature of the water. Once the water absorbs the heat, its temperature increases. We can get to know what is the final temperature of the water. through a thermocouple based on the difference in the temperature and then the known volume of water that we have taken. We can quantify how much amount of the heat is released by the combustion of your waste material. So that is what actually goes as the working principle for your bomb calorimeter. The heat that gets released during the combustion is nothing but it's equal to the heat gained by the bomb and the water. And that's how this expression is usually represented. Heat released is usually represented in the form of enthalpy, that is delta H is equal to the heat gained by the bomb as well as the water. So MB CPB delta T plus MW CPW delta T, and then if you simplify, what you get is delta H is equal to W times delta T, where delta T is the final temperature minus the initial temperature and W is the water equivalent. MB is basically the mass of the bomb, MW is mass of the water that we have taken, CPB and CPW. What are those values? CPB and CPW? Yes, CPB and CPW. So I would like all of you to actually search what is the meaning of CPB and CPW. Oh, I think I received a response. Specific heat value, exactly. So CPB is the specific heat value of your bomb and the CPW is the specific heat value of your of the water. So this is so bomb calorimeter is basically the technique by which you can get to know the heating value of your waste material. So if suppose somebody asks how much amount of heat energy is going to get released, then this is basically the process through which you can quantify the heat generated. And how we can quantify heat? Heat is usually quantified as a function of temperature. So this place we end our discussion on the course this thing. Next we will actually move towards solving problems. So if you have any doubts, you are welcome to discuss right now, or otherwise we can progress further. So in this particular slide we will be discussing more in detail. So this slide will take quite some time compared to other. Again, I think we have approximately 45-50 minutes in our hands, so that would be sufficient. So in case if you have nothing to ask, shall we move forward with these questions? For those of you who want to discuss something, then you please feel free to unmute yourself and then speak, or to ask your doubts, or else you can also use the chat box. For those, for the rest of those who do not have anything to discuss right now, you can go forward with these questions. So let me just read out the question first. Question number one is, which of the following density includes both the pores and the interparticle spaces in the system? You have four different types of density. So In the third slide that we discussed, we usually told density as a single entity, but we in density we have totally three different types of density. So each and every particular type of density comes with certain conditions, whether to include or exclude few parameters. So based on that, we are supposed to tell which of the following density here includes both pores and interparticle spaces in the system. First one is bulk density, second one is true density, third one is apparent density, and fourth one is envelope density. This kind of classification of density is very important to know, because when you deal with um, porous samples, or you can even say powder samples, depending upon the type of geometries that you choose, the density can actually vary. So when you compare materials, you need to be careful on what kind of density is being discussed. So there may be materials like porous foams, which may be very light in weight because of their porous nature, and you may also come across powder materials which are usually converted in the form of pellet by compressing them. So in that case their density actually varies, differs. So it's actually very important to know the terminologies, so that in the future, anytime in the future, it will be useful while comparing different types of materials based on their density. Specifically, this becomes important when you deal with waste materials. So when you actually try to convert these waste materials, you need to be careful about the different types of densities that you encounter. So which of the following includes both pores and interparticle spaces in the system? Any answers? Oh, okay. There are a lot of answers that's actually generated. Bulk density. Yes, bulk density is correct. So if bulk density is the one that is going to include both pores and the interparticle spaces in the system, then also we need to see the other options as well. So if bulk density is the density which include both pores and interparticle spaces, then what about true density, apparent density, and envelope density? I mean, which parameter gets included or excluded in the other three cases? Any answers? Okay, this I agree. It includes both pores and interparticle spaces. But what about the other three? What about true density? Apparent does not include. Okay. I mean, does not include both pores as well as interparticle spaces, or so true density is the one that is going to actually exclude both. Am I right? Exclude both your pores and interparticle spaces. So that is the true density, or it also has an another name, which is the absolute density. Then what about apparent density and envelope density? Anyone? Pores and spaces. Oh, no, actually, apparent density, it is true density which does not include both your pores and spaces. Apparent density includes your pores but excludes your interparticle spaces. So, but again, please correct me if I am wrong, because this terminology remains confusing to everyone. Is this fine, whatever I have written for the first three options? This is excludes both. This is includes pores but excludes the interparticle spaces. Then what about envelope density? Envelope density. Envelope density is same as apparent density. It's just an alternate name for apparent density. So this is about the density, the very first physical properties that we discussed in today's session. So in that density we have totally three different classification. One is your bulk density, which include both pores and interparticle spaces present in the system. Then it comes your true density, or true density can also be called as absolute density, which excludes both pores and interparticle spaces in the system. Then you have your apparent density, which include pores but excludes interparticle spaces. Alternate term for apparent density is nothing but it is your envelope density as well. Now here I have one question which I want you people to tell me, what is actually the difference between pores and interparticle spaces? Aren't they same, or are they different? Pores and interparticle spaces, whether they are different or whether they are the same. Anyone here who exactly know the difference? Pores and interspaces are the same. Okay. So then if they are going to be the same, then I don't. So yeah. Uh, then why do we classify them as two different words? I could have just simply wrote pores and pores. Just that's one term, right? If both pores and interspaces are same, so they are not the same. But what is it that is different in pores and interspaces? They are not the same. Pores and interspaces are not the same. Okay, interspaces are the gap between the particles. So if that is true, then what are pores? Pores are the free openings. Hmm. Try to look at the definition for pores and interparticle spaces. Again, they are not the same. So that one thing I can clarify right now. But I want you actually to, all of you to actually go out and look what is the difference between interparticle spaces and pores, because we will deal with many materials, as I mean, not just related to this course but even in outside of this course. We talk about engineering materials, we will deal with such a wide variety, versatile class of materials, that they will have both pores, interparticle spaces. So these terms, some places they may use alternate as synonyms, but they are not the same. So we need to have a clear cut understanding on what is pores and what is interparticle spaces. So but before that, I encourage all of you to actually go out and look what exactly is the meaning of interparticle spaces, and what is the meaning of pores, and how both of them are different from each other. So I will ask this question in the next live interaction session as well. So I will note it down here, how pores and interparticle spaces are different. So I think I received a comment. Pores are openings outside the particles. Then they are interparticle spaces, right? If they are going to be outside of the particles, then wouldn't I tell them as interparticle spaces? That's all. So uh, please look at it and let's discuss that particular difference in the next live interaction session. So coming to question 2, measurement of density can be done by which of the following? Pyrometer, pycnometer, anemometer, and then none of these. So I think one of the answers were pycnometer. Okay, so I hope everyone agrees it's pycnometer. We measure density based on pycnometer. Can anyone tell me what is the working principle behind this pycnometer, or how does this pycnometer work? There is a particular principle behind the working of a pycnometer to measure the density of the sample. So how does that work? Working principle of pycnometer. Archimedes principle. Can anyone tell me what is Archimedes principle? Okay. Um, so if pycnometer is for measuring density, what about options A and C? What is the use of pyrometer and what is the use of anemometer? Eh, Pyrometer and anemometer. I mean, they are also used to measure other physical variables, but what are they? What are the parameters or the physical quantities for which these particular instruments are used? Uh, As Karthik rightly said, Archimedes' principle states that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially, is equal to the weight of the fluid that the body displaces. Yes, so that's correct. So it just to refresh what we already know. So now coming to this, what is the use of pyrometer and anemometer? Yes, anemometer is used to measure the wind speed. That's exactly correct. It's something that if you can, this is something that the meteorological departments usually use the anemometer to identify the wind speed as well as the direction, or you can say the wind velocity to be to state it. Then the use of pyrometer. Again, anemometer is if you are able to tell, then pyrometer should be very easy. Pyrometer. So, what is the meaning of the word pyro? It's used to measure temperature. So that is what is a pyrometer is. So let's move on to next question. I hope nothing much is as a doubt here. Oh. Yes, pyrometers are usually used for measuring temperatures when they are high. If the temperatures are low, then I mean less than 100 degrees Celsius, then you can use a laboratory thermometer or a clinical thermometer. But when the temperatures goes high beyond 100 or 200 degrees Celsius, then for measuring those kind of temperatures, you usually use a pyrometer. Third one is hydraulic conductivity of MSW depends on its dash. What is MSW? Municipal solid waste. So now what is hydraulic conductivity now? The question is. So hydraulic conductivity is nothing but it is usually the ability of your porous media to conduct the liquid. So the leach, in case of the landfill leachate, whatever that gets generated, it has to actually go through a series of layers of the surface before it percolates. So that particular conductivity or permeability is what you call it as a hydraulic conductivity. Now this hydraulic conductivity depends upon many factors. Among them, the two are particle size and fabric. The other factors, particle size is one, fabric is one, then the third one is degree of saturation, and the fourth one is pore geometry. So, other than these, pore geometry is also one of the factors, and degree of saturation. How far the layers are saturated. So that's what this typically represents. Now let's, if you have any doubts, you're welcome to unmute yourself and then speak up, or you can post it in the chat box. I think these questions should be quite simple. So, based on the sources of occurrence, solid waste can be classified as. Now only we discussed this. We discussed three types of classification of solid waste. One is based on their source, second one is based on their usability, third one is based on their degradability. So this is based on the source. It's all of the above. Didn't I write it here? Oh, so let me just write this. Based on source, you have municipal, industrial, and agriculture agro. I am going to write based on usability of organic recyclables and inerts, and based on biodegradability it is either biodegradable or non biodegradable. Now before moving on to this question 5 and 6, let's see question number 7. We can use melting point rather than boiling point. Yes, that is also one of the physical properties in case of solid waste, to know at what temperature does this solid gets melted. So that is absolutely one of the physical properties which will be of importance to us. So identify the following apparatus in the figure below. Is it a distillation column or a sieve analyzer or a ball mill? So when we discussed about this physical properties, we for the time being we have discussed about density, then we discussed about moisture content to some extent, and then we discussed about hydraulic conductivity. So one thing that was left out is particle size distribution. It's a sieve analyzer. Okay. It's a sieve analyzer. So apart from so sieve analyzer as such, it is basically used for separating the particles of different shapes and sizes. So you use a series of filters, and based on the different types of sizes and particle shape, certain fraction of the solids gets accumulated in each filter, and based on that you can plot a particle size distribution. Again, apart from this sieve analyzer, you also have two other different types of equipments to basically um, analyze or to basically do the particle size distribution analysis. One is your particle size analyzer itself, which is used for very small particles which you cannot do it manually through sieve analyzer, and for big as well as coarse particles you use something called as a throttle. For intermediate particles you use something so called as a sieve analyzer. So if sieve analyzer is used for particle size distribution, then what is the use of distillation column and ball mill? Any idea on that? Ball mill and distillation column. So let me just do one thing. Let me stop sharing for 1 second and let me present it again. Yes. Mm. Is my presentation visible? Okay. Okay. So distillation column, as someone said, it is. Wait, just a second. I will. Yeah. So, okay. So, as someone said, distillation column separates the given material into different fractions based on the boiling point ranges. That's true. Ball mills are used to reduce the coal sizes in the. Basically, it is used to reduce the size of a particle in general, and distillation column, yes, it is used to separate two different kinds of materials or a given material into different fractions based on their boiling point ranges. So that is fine. Now the last question for this MCQ. Before we progress, we have two problems to solve. So gasification and pyrolysis process for energy production from biomass and waste are associated with. Choose the most suitable options. Identify the most suitable options. I think I received uh, thermochemical. Yes, it's called thermochemical conversion technique. So because again in gasification and pyrolysis, both the process, you usually use temperature to burn the material, but there is a difference between gasification and pyrolysis. We will discuss the specifics of this in the next live interaction session. That is where we will totally dedicate our entire next week live interaction session on understanding the difference understanding the difference of burning a material, how burning one particular waste material can be actually classified into three different ways based on a particular factor. So that we will deal with the next in the next session. So for this particular question, gasification and pyrolysis are the examples of thermochemical conversions. So next question, let's, I hope there are no doubts. If you have any, please let me know, or otherwise we can move forward. Actually, there is one particular question which needs to be done. Okay, so let me just check once. Okay, so let's do question number 4. First question. Let's talk about the second question later. Probably either if we have time left out today or in the next class. But what about the first question? Weight fraction of a uh, oh, sorry, there was a network disruption. So I hope my screen is visible. So the first question is, calculate the weight fraction of the moisture content in a biomass sample. The weight of the biomass waste before moisture removal was 9.23 and the weight of the biomass after moisture removal is 6.565. Now you need to calculate the weight fraction. If anyone has calculated, 28.873 percentage. Okay, or 0.288. Any other answers? 54.06. Oh, that's double the value of what it was. So what's the formula? So let me write this. Percentage moisture is equal to weight of biomass before moisture minus weight of biomass after moisture removal divided by what should be the denominator? Should the denominator be weight of the biomass after moisture removal or weight of the moisture before moisture removal? Sorry, weight of the waste before moisture removal. Before moisture removal. Ah, original weight. So based on this, then what will be the answer? So percentage moisture is 9.23 minus 6.565 by 9.23. So what will be the value? Let me use calculator. 28.87. You can say 0.2887 or 28.87 percentage. Is this all fine or are there any other different answers apart from what we have written here? Any other different answers? Same answer is correct. Okay. Okay, so the percentage of moisture is going to be 28.87 percentage. Now let's skip these questions and let's go to question 7. So it's about the bomb calorimeter concept that we discussed. A solid waste is there and it has 1% sulfur content. It is combusted in a bomb calorimeter. The temperature of the bucket water or that water that we know increases from 25 to 30 degrees Celsius. The water equivalent of the calorimeter is 2402 calories per degree Celsius. 1.5 gram of sample is used for the test, and par 45 C10 wire is used for ignition. It was observed that 5.4 centimeter of the 10 centimeter wire is burnt. To titrate the calorimeter, we use 24.2 ml of washing sodium carbonate with this particular molarity of 0.0709 normality. Calculate the gross heating value of the waste in joules per gram. Consider that the thermometers are working perfectly fine. Now you are supposed to calculate the gross heating value, that is nothing but it is your delta H. So how do you calculate this? We will end our discussion with this particular question. There are two more. This is quite simple, so we will take up this in the next class, or probably I will give these questions as a kind of task which you can use to practice outside this session. Gross heating value. Just a second. Okay. So what's the formula to okay, I think. Okay, somebody has told 7956 calorie per gram. I don't know, I do not have the answer, so let's start calculating that. Just a second. So what's the formula? If I'm making any mistakes, then please correct me. Where is delta? Yeah. Is this fine? Hg, the gross heating value is nothing but it is water equivalent times delta t minus the three correction factors E1, E2, E3 divided by the mass of the sample that you are going to use for your test. So water equivalent is given 2402 calorie per degree Celsius. Delta T is TF minus TI. So TF is 30 minus 25. What about the values of E1, E2 and E3 divided by M is 1.5 grams, so 1.5. What are the values of E1, E2 and E3? Okay, E1, E2, E3 values. E1 is 24.2. E1 is 2402. Is it 24.2 or 2402? E2 is 13.7 times 1. Just a second. Shouldn't there be a 1.5 as well here? And what is the value of E3? Since we use par 45C10 nickel chromium wire, it will be 2.3 times C3. What is the value of C3 here? C3 5.4. Because here 5.4 centimeter of your wire is going to get burnt, so you should use that. If suppose the question says that it was observed that 5.4 centimeter of that 10 centimeter wire is left out unused, then it will be 10 point then it will be 10 minus 5.4. But since this much amount of the wire is burnt, so we take that into consideration here. So what will be the values? 13.7 times 1.5, 20.55, and 2.3 times 5.4, 12.42. So if you subtract, I mean if you do this 0.2 times 5 minus 24.2 minus 20.55 minus 12.42 by 1.5. What is the value? 2402 minus 24.2 minus 20.55 minus 12.42, this divided by 1.5, 7968.55. This is in what units? Calorie per grams. Yes. But if you see the question states calculate the gross heating value of the waste in joules per grams. So we need to convert calorie into joules. So then what will be the conversion unit? 1 cal is how many joules? 1 calorie is how many joules? 4.184. So then the value of Hg will be this entire value divided by 4.184. 1904.53 joule per gram. It is 4.184, and I think there is probably that decimal error. So kindly check that. So this is the value of Hg. So is there any doubt related to solving of this problem, or we have few more? So um, like for example question 2, question 6 and question 8. Out of these questions are all these questions are all straightforward questions. I mean, if you see, for example, let me just read out question 2. You have a biomass sample of a particular weight. That biomass sample is heated to remove the moisture, and it is told that 25% of the sample is going to be lost as moisture. Now the bone dry sample, that is after all the moisture that gets removed, whatever that sample that is left out is called as a bone dry sample, is going to be burnt at 1000 degrees Celsius to derive energy from the biomass or the waste. The ash, whatever that is left out after burning, is recovered and its weight is measured as 2.53 grams. You are supposed to calculate the percentage of ash, but here that calculation is going to be based on the moisture free sample. So so I think it's going to be straightforward. So percentage of ash is nothing but it's going to be weight of ash divided by the weight of the bone dry sample. uh, how do you calculate the weight of bone dry sample? That is nothing but 6.24 weight of your biomass sample minus 0.25 times 6.24, that is the moisture. So weight of your biomass sample minus the weight of the moisture contained in the biomass sample will give you the weight of the bone dry sample. That's going to be the denominator, and the weight of the ash is already given in the question, so you can easily calculate the percentage. And since our basis is moisture free samples, we use the denominator as the weight of bone dry sample. If it is based on the if it is wet basis, then you can use the original weight of the biomass sample as such. So like this only those two questions are also going to be. So if you have any doubts, then you are welcome to ask me now. Any queries? Oh, yeah, there's one question. Yes, so what is the doubt, Sri Karthik? I mean, you have told that I have one doubt on previous question. We need to find the percentage of ash, but I mean, what is the Ash, 45.9% someone has told. I do not have the answer, so uh, again let me just calculate it here. So percentage of ash is going to be 2.53 divided by 0.75 times of 6.24. Is it 45.9 or 50.05 percentage ash content? Yeah, it is 50.06 percentage. Even I am getting ash content as 54.06. So please check the ash content value is 6 point sorry 54.06 percentage content percent. So I think let me stop sharing. So if you have any doubts, you are welcome to ask me now. And also, since this is our very first live interaction session and this course is for 8 weeks, so we will be meeting on every Sunday. So I also want, like kind of comments. If you have any comments or feedbacks related to how this presentation is going on, you're welcome to share it with me here, so that we can modify it as per the requirements. So any feedbacks or any comment on the way the presentation was carried out, like the pace of discussion, or do you want more amount of time dedicated for problem solving, more amount number of numericals, or more number of theoretical questions? So if you have any kind of feedbacks like that, then please feel free to share it. Either you can unmute yourself or you can type it in the chat box. So this particular session is actually getting recorded. So this recording along with the presentation will be available to you by mid next week maximum. This particular session recording and the presentation, you can actually access it through the NPTEL course page. So if you visit the NPTEL page for this particular course, in the left hand side, in the at the bottom you can see problem solving session 2026. So if you click on that, you will be directed towards an Excel sheet where you will be able to access the video which will be uploaded in the YouTube along with the presentation. So in the presentation, my email ID will also be there. So in case if you have any doubts during the week, you're feel free to email to me. I'll be able to answer to your queries as soon as possible. In case if the query is of great importance and it requires discussion in the class, then I'll take it during the interaction session itself. So So in case if you have no queries or any comments, so I think we can conclude our session for today. So thank you all for joining today's live interaction session. Our next live interaction session will be on 1st February, that is Sunday, from 5 p.m. to 7 p.m. same time. I also take this as an opportunity to thank the Professor Prasenjit Mondal sir, and the NPTEL team for providing me this opportunity to interact with you all in this Sunday afternoon. So, thank you so much for joining and have a great week ahead. And thank you and bye.